so today we're going to revise our view of the atom. Remember, we've been lying a little bit less every single time with our view. Our last view of the atom was the Bohr model. And so we want you to watch this video here on how they came up with the idea that there's different energy levels in the atom. So let's take a look at that and we'll talk about it right after.
If a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you'll see an emission spectrum consisting of bright lines at specific frequencies. Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the element. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.
So, Mr. Dimitrowicz, we've got this spectrum of hydrogen. So explain how that works, because it kind of works in the level of the atom, right, with our 7 levels.
So every time, and this, you remember the very first video that we did before, which is, thank you, the video we did before on the staircase, where every time you jumped up, nothing happened. When you fell back down, you gave off energy.
Right.
Every time an electron jumps up, and you need to understand that because they're moving so quickly, an electron's going to jump to every single orbit or energy level over and over again and fall back down. So if I'm in the 7th energy level, I have these possible fall downs. Can I go 7 to 6,
yep.
7 to 5, 7 to 4? Each one of those is going to correspond.
So that'd be 7 different options.
7 different options. But
6 can go to 5, 4, 3, 2, 1. And so it's this finite number. How many are there?
There's only 21
options.
21 possible
But
drop downs.
So on this picture, I only see 4 lines. So what's up with that?
So here's the thing. Every single drop down releases energy, but not all energy we can see. Remember, we only see a very small amount, the visible spectrum,
so
right?
There's 4, and if there's 21 options, the other ones are maybe ultraviolet or an X-ray or something like that.
We just can't see them.
We just can't see them.
So
that works.
Yeah,
okay.
and the model of the atoms, we're like, ka-check, that looks really good.
Great, but that's hydrogen. But now we've got iron right here. Now that just, whoa! That's more than 21.
Yeah. So here's the problem. If the view of the atom says there's only 7 energy levels, right? And that means there's only possibly 21 drop downs, and we look at this monstrosity right here.
There's more than 21 lines right there. Like I go 1, 2, 3, 4.
So what does that mean? It must mean therefore that there must be more
levels.
There must be more than 7. And so the new view of the atom that we're going to talk about is the idea that, yeah, there's 7 main energy levels, but there's also
sub-levels. So there's levels and there's sub-levels. I know it's confusing, and actually they take the form of some shapes, which we'll talk about later. It's crazy, weird, but super awesome at the same time.
Yeah, it's going to be really cool, and we're going to move from the realm of flat, two-dimensional, hey, I'm an electron traveling in an orbit, to this idea that you can actually live in an orbital home, a 3-dimensional region, because everything around us is kind of 3-dimensional. So even though we've been lying a little bit less every time, we actually have to know something about waves, which we talked about in the previous video, to be able to understand how electrons work. Because, and this is crazy and kooky, electrons travel sometimes as a wave, and sometimes that's like this, and sometimes they travel as a particle. This video that I want to show you right now, it's probably the best we've seen at trying to explain this. Again, grab onto something, because this is entering into kooky world. And once we get done with this, even if you don't understand it, because let's be honest, the best physicists in the world and chemists in the world don't even understand it fully, we'll have a better tool chest to be able to start explaining how that.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So yeah, we've got these more than 7 levels, right? That's the summary. And then I've got these electrons. And it's weird that we're talking about light and electrons at the same time. But that's because of this wave-particle duality that we just saw. See, the electron falls. When he falls to this level, he gives off light. And I draw a wavy thing because it comes out as light. But it's also sort of a particle. It's just this weird, crazy idea. And again, to add more complexity and just to blow your brain cells, you know, you've got this little electron right here. And then when he jumps up to the higher level, remember there's no point or moment in time when he is up here. to understand the idea of quantum, I think there's an interesting old TV show, 80s or 90s, called Quantum Leap. And the storyline was this: the hero or the main protagonist in the story, he would jump between time. So he'd start in 1992 or whatever the season was, and he would go back into time. He'd meet Abraham Lincoln in 1862 or something like that. But when he was jumping from 1992 to 1862, he was never in 1953. He just immediately appeared in 1862. And that's kind of the idea. So the term quantum leap made sense. He was leaping between times, and we know you can't do that in time, but atoms or electrons in atoms do that. They jump from level to level, and now not just level 1 through 7, but our more complex levels that we'll learn about later.
So hopefully in the future we'll reference other defunct shows that will help you with our learning process.
It's kind of a fun show. I bet you could find it somewhere on
Yeah,
YouTube.
it is not aged well. I do recall. I think it's
Probably
actually on
not.
Netflix. But spoiler for the next episode of our own private video channel here is that we're going to be talking about how that actually makes our atom look. Now, if you don't get everything that we've just talked about and the idea of being in one place and another at the same time, join the club. We're in that same boat. But what you will learn is how electrons live in these shaped orbitals, and that's what we're going to look forward to doing.
We'll see you in class.
Indeed.
Now, the best
I love
video
that
I
fun.
used to show.
I'm going to go find that video right now before I forget it.